Good morning, Calculus. Uh, we're here to talk about derivatives today, and not just derivatives and easy rules and stuff that you probably already know, but we're going to go through a few questions that are a little tricky. Um, you should have this piece of paper in front of you. If you don't, let's pause the video, make sure you get it there, because you're going to want to take some notes on this, and there will be some times where we do problems together. If I go too fast, the video will be linked on the key on the next page, so you'll have access to that, and the key will be on the next page as well. So I wanted to start with a bunch of derivative rules here, and I realized, I copied it over. I was like, oh, this is exactly what I want. Great. I printed out this page, and then I realized this is not the chart I wanted to put on here. So I just wanted to emphasize that you have these. These are close, but they aren't exactly what you're looking for or what we're used to. For example, all of these in the right column, the rule itself is correct, but they're all treating u as a separate variable, as in we're doing implicit differentiation on every single one of those. So the rules themselves are still correct. So the derivative of cotangent is definitely still negative cosecant. That's right. But, sorry, this part's right in my pen. Oh, come on now. Tried to use the soft pen, it's not working that great. Oh, we'll figure it out. The derivative of cotangent is negative cosecant squared, but generally we don't need that du dx unless we're doing implicit differentiation. So the rules themselves are good. I would reference your colored sheet. Don't stress too much about this. It's there to remind you that these are all things that we know. We did learn these. We do know these. They're in your brains. They're deep in the recesses here, but we need to have them at the forefront by the time we get to the calc test. So with that in mind, I want you to look at this yellow box on the screen. For you, it printed pretty dark. It's a pretty shaded box. We know a ton of ways to take derivatives, a ton of ways. And I want you to take about 15 to 20 seconds here and list out all the ways you can think to take derivatives. So uh, our sub in the room, please pause the video here for a second. Let's let students take like 30 seconds, write down every way you can think of to take derivatives. Ready, go. All right, hope you got a bunch of them. Take a sneaky peek over at your neighbor's page to see if they have some that you don't. Add that to your list. You might have some that I didn't list. This is the problem with doing this on video, is that maybe you had some that I'm not going to think of right here, right now, or that I, thought of before. But here's some ways I can think of to take derivatives. You could use the power rule. That's one way. That's the easiest way. You could use the chain rule. You could use the product rule. You could use the quotient rule. All of these are specific rules we know. They used to be on that poster on the back wall. Hope you didn't just look back there right now because they're not there anymore. These are all the special rules we learned in Unit 2 and 3. Let's see. We learned how to do implicit differentiation. That's when we had derivatives of y's or different variables. I'm going to include this as a separate rule, but we did also learn how to do derivatives of inverse functions. And that's one thing we'll talk about here today is inverse function derivatives. That was its own special rule that doesn't fit into these. We'll say inverse trig also maybe fits in here. Or maybe we should have listed this as like special trig rules or something like that. We also knew one final thing you could write down is just to take multiple derivatives. So that is something that you could see is like, hey, take 12 derivatives of this function. Doing it over and over and over again just to make sure we've got the ideas of derivatives in our head. So these are these are the 6 that I could come up with. There are probably others that you came up with. If so, awesome. Send me a Teams message. I'll make sure to think about that and include it. But we're going to do a few practice problems, specifically focusing on combo derivatives, which is like a number 2. Focusing on inverse derivatives, inverse functions, which is this 4th one here. And then focusing on implicit differentiation again, because that's something that's pretty hard for us. So these are my 3 foci for today. and we'll definitely do one problem from each, and we'll do one equation of a tangent line problem just to make sure that's still in our brains. So 4 problems together. This is the first one. I think this is the only one on the front. Let's talk about it here. So I really wanted to emphasize this because this is something that should be automatic. Anytime you see the equation of the line tangent to the graph, you should almost start by tossing your point slope form on your paper. Equation of a line tangent to the graph. Start out y minus y1 equals m times x minus x1. Start there every time. I need a point and I need a slope. Luckily, I already have a point. My point is 0, 1. I've seen some of us mix this up recently. The 0 and the 1, we plug those in for our y1 and our x1 value. Because we still need to have an xy combo to generate points on this line. So I still need to keep an x and a y. The point gets plugged in for x1, y1 because that's a kind of an initial condition, I guess. It's one we have already. Next, we just need that m. M is just slope, right? So take a derivative, plug in your x value. This is something that, like we've talked about, the calculus isn't too hard, but you've just got so much to remember that sometimes this can be tricky. So let's take a derivative. Y prime equals 1. Derivative cosine is negative sine of x. And then we're plugging in the x value to generate our slope. So y prime 1 minus sine of 0 is 0, so our slope is just 1. There's our equation of our tangent line. Write out point slope form, find an xy pair, find a slope, plug them all into the correct spots. Just wanted to refresh your brains on that. Number 2, so this, again, the second topic we're going to cover is chain product and quotient rule, and specifically using them in slightly different ways. So I think we're pretty solid with product rule, we're pretty solid with chain rule, and we're pretty solid with quotient rule when it's just asking us to do those things. Our issue is, number 1, if we have to combine them, that's hard. And then number 2, if it asks us to just do something a little bit different. So that's why I want to do this problem here right now. So flip your page over. This is on the back of your paper. It gives us a function, and it says, what points on the graph have the property that the line tangent to f at the point has a slope of 1/2. So again, anytime we think slope, we're thinking derivative. And so essentially we're looking for our points where the derivative is equal to 1/2. So here's what I'm thinking. I'm thinking, let's take the derivative of f of x, let's set it equal to 1/2, we'll solve for x, and then we'll plug that back in to find our y. That's my general game plan here. Take a derivative, set it equal to 1/2, solve for x, plug x back in to find y. If I take a derivative, this is a fraction, so that's why we have to do our quotient rule. That's why I've included this problem here. So f prime of x. Quotient rule says derivative of the top, keep the bottom the same, minus the top times derivative of the bottom, all over the bottom function squared. So here's our derivative. I'm going to simplify a little bit on top, and I'm going to set it equal to 1/2. So we'll rewrite this here as x plus 2 minus x over x plus 2 squared equals 1/2. X minus x is 0, so on top I just have 2 over x plus 2 squared equals 1 over 2. And you could cross multiply, you could use some logic here, but essentially we're saying x plus 2 squared has to equal 4. So maybe you multiply the right side by 2 over 2, and then you set the denominators equal. Maybe we just cross multiply. Regardless, we're going to say x plus 2 squared equals 4. I'm going to take the square root of both sides, but this is where we got to include positive 4, or excuse me, positive 2 or negative 2. Anytime we take a square root, if we're taking the square root, we've got to include plus or minus. So let's solve both of these for x. On the left I get x equals 0, on the right I get x equals negative 4. Those are my two x values, but those aren't points, right? So I just need to plug those in. I don't really even need to. I can see that my options here where I have 0 and negative 4 is C. I definitely see that that exists, but let's just look up here. Would these points work? So if I plug 0 in, it would be 0 over 2. Okay, that's fine. If I plug negative 4 in, it's negative 4 over negative 2. Yeah, that's fine too. That still works, right? So C is our solution here, and we're good to go. Tricky chain product quotient rule problems will definitely come up. Let's look at number 3. Number 3 is quicker than it looks because it looks pretty nasty. So pause for a second here, think about this one. Let's pause, Proctor in the room here, and just make sure everyone's on, able to take a breath. Okay. We gotta find g prime of 1, and it says that g is the inverse function of f. So we learned this a long time ago, but there is a rule for inverse derivatives. Essentially, if I want to find g prime of 1, I'm trying to find f inverse prime of 1. And this is where our rule comes into play. So you wrote this down on that colored piece of paper from the beginning of the year. Every time we're trying to do inverse derivatives, the formula that we have to remember is 1 over f prime of f inverse of x, or in this case it's just 1. And now we just have to solve for the two missing values. So we have to find f inverse of 1, and then whatever we get, we plug that into f prime. We want to know f inverse of 1 equals something. That's our goal. But we do have this point, and this point says f of 0 equals 1. So it turns out that inverses swap inputs and outputs. So if f of 0 equals 1, then f inverse of 1 equals 0. Yeah, nice job. So rewrite this on a new line. 1 over f prime of 0. Now we'll go up, take that derivative, plug in 0 for x, and evaluate from there. This was a multiple choice question that I just cut off for space. But these are, if you got the equation right, generally they're just testing, do you know the equation? They're not trying to trick you with some crazy possibilities, right? So the derivative here, this is a chain rule derivative. Derivative of the outside, keep the inside the same, multiply by derivative of the inside, and then f prime of 0, that's what I want. Plug in 0 for x, so 3 times 1 squared times 2, that's just 6. So 1 over f prime of 0 is 1 over 6, and that's my final answer. That's my inverse derivative using the function that we learned months and months ago. There's one more question here. I'm at 14 minutes, and this free software I use has a timer of 15. So I'm going to pause and pick up the last question on the next video. Hope the first 3 went okay.